Hi everyone, my name is Sean.
My name is Ahmed, and we're Team HTTP 404.
What if we could measure water quality in rivers that have never been tested? In South Africa, millions of people rely on water sources that are really monitored, not because it's unimportant, but because it's expensive and sparse.
Water quality monitoring today depends on physical sampling, which is costly, infrequent, and limited to a small number of locations. In this competition, we were only given data from just 162 monitoring stations, but asked to predict water quality at entirely unseen locations.
Zero overlap, no direct measurements, only data and physics. This is fundamentally hard because most machine learning models rely on seeing similar locations during the training. Here, the model must generalize to entire new rivers with different geology, climate, and human activities. Our key insight is simple. Rivers that are geographically close tend to behave similar. So instead of predicting water quality in isolation, we asked, what can nearby rivers tell us?
In order to accomplish this, we developed Geographic K-nearest neighbors meta features. For any location, we identify nearby monitored rivers and compute distance-weighted summaries of their water quality. Geographic and environmental distances alone are only moderately correlated. Nearby stations may be in different environments, and distant stations might actually have similar conditions. Using KNN meta features allows us to create a spatial interpolation framework that captures a core principle of our approach, that nearby rivers share geological and hydrological characteristics, while blending geographic neighbors with environmentally similar but physically distant stations. This accounts for the moderate correlation, and is especially valuable for predicting results in the validation set, where the nearest training stations may be in different biomes, but environmentally similar stations exist further away. We used multiple k-scales, from k equals 1 for hyperlocal geology to k equals 30 for regional trends, and fed all of this into a regularized XGBoost model, which is naturally able to capture complex interactions, manage nonlinear feature relationships, and handle missing values and outliers. Through this, we can begin to achieve robust spatial generalization. What makes this powerful is that we're not just using nearby rivers, we're encoding how they behave over time, their statistical patterns, and using that as input into the model.
To ensure real-world performance, we simulate the unseen scenario during the training process. By removing each station from its own neighborhood, we prevent data leakage and force the model to learn transferable relationships.
We combine this spatial intelligence with satellite and climate data, including rainfall, soil moisture, and land characteristics, capturing both environmental drivers and geographic similarity.
We tested over 100 approaches, and many failed. For example, raw location features often caused overfitting, while carefully engineered spatial and satellite features generalized much better.
Our final model achieved an R-squared value of approximately 0.69, which represents a 240% improvement over the benchmark score. But beyond accuracy, the real impact is what this enables. Instead of monitoring a few hundred locations once a month, we can estimate water quality at thousands of locations every 16 days, at a near zero marginal cost.
This enables earlier detection of contaminations, better allocation of limited resources, and expanded coverage to underserved communities. The challenge pushed us to rethink machine learning in the space.
Not just fitting patterns, but learning relationships that generalize.
We didn't just build a model, we built a scalable framework for water monitoring.
Thank you.
Good job.